Hi, in this video we are going to talk about cuts. So let's get started. Basically, what is a cut? A cut, called ST of a flow network G with vertices V and edges E, is a partition of vertices such that every vertex will belong to either S or T. For example, we are able to construct two sets out of this flow network where the A, the B, and the source is going to be in the set S, and the D, C, and the thing is going to be in the other set called T. Or for example, we are able to construct a cut like this. So the source and the vertex A is in the first set, and the B, D, C, and the thing is in the other set. Or we are able to make a cut like this, that the A, B, C, D, and the source is in the first set, and the T, so the thing, is the only vertex in the other set. Okay. And basically another important expression is the so-called flow across the cut. So we add up all flows going from one set of vertices to the other. So for example, from S to T. So let's consider the fact that we have this cut. So we have the source and the vertex A in the first set, and the C, B, D, and the thing in the other set. And we would like to calculate the flow F for this cut. We just have to consider every outgoing edge that's going to be positive and every incoming edge. And because the incoming edge is in the opposite direction, that's why we are going to use numbers smaller than 0 in this case. So let's consider the fact that, for example, we have the outgoing edges with the flow 6, and the other outgoing edges is the flow 3. We don't have to consider this edge. By the way, we can consider it with the flow 4, but because of the skew property, it's going to be 0, because we have 4 units of flow going from S, so basically it's going to be plus 4, but as far as the vertex A is concerned, it's going to be minus 4 in the aspect of this vertex. So we don't have to bother about edges in between vertices from the same set. Okay, so we just have two edges pointing from a single set to another set. So from the set S to the set T. And the other edge is this one with flow parameter 3. So we have 3 plus 6 outgoing flow, and we have a single edge with the flow parameter 2 as an incoming flow. So the overall flow of the cut is the outgoing minus the incoming, which is going to be equal to 9 minus 2. So we have the answer. What is the flow F of this cut? It is 7. And this cut is quite important because it has something to do with the maximum flow. And by the way, these cuts are quite important because it has something to do with maximum flow. So we can pose the question that what's the capacity of this cut? So instead of the flows, we have to consider capacities, and we can come to the conclusion that the outgoing capacities are equal to 5 plus 7. And the incoming capacity is equal to 3. So the overall capacity is going to be 9. Okay. And I would like to tell a few words about the max flow and min cut theorem. As I said earlier, the flow is not independent from the cut. So the value of any flow is bounded by the capacity of any cut. So the maximum flow and the minimum cut have something to do with each other. Just to be precise, the value of the maximum flow passing from source S to thing T is equal to the value of the minimum cut. So the total weight of edges in the minimum cut basically. Another important fact is that the minimum cut is the smallest total weight of the edges, which if removed would disconnect the source from the thing. Okay, but what's very important is that max flow min cut theorem, that basically if it's easier to find the minimal cut, then we have to look for the minimum cut, because we know for certain that the minimum cut is equal to the maximum flow. Or if we would like to find the minimum cut, but it's much more easier algorithmically to find the maximum flow, then we have to look for the maximum flow because we know for certain that the maximum flow is equal to the minimum cut. This is the so-called max flow mean cut theorem. Thanks for watching.